So let's consider what can we do with the inverse of the trigonometric functions. There's a couple of things that can work in the same setup that we work with trigonometric functions, which is in applications that uses the right triangle. So as an example, consider ballpark, and the sun is descending behind the 150 feet grandstand of the baseball stadium. So you can see that the sun is casting its light over the stadium, and the shadow of the stadium is moving across the field. So you can see over here how the shadow is moving across the field, and we're going to call L the segment of line between the edge of the shadow here and the sun, and theta is going to be the angle of elevation of the sun in the horizontal line. Okay, now the shadow length is this distance x, and it comes from here, from the edge of the shadow and the base of the grandstand. Now we can describe the movement of the angle of elevation theta. We can describe that if we take into account the trigonometry of the right triangle. Notice that because this is a right triangle, we can account for theta as in terms of the sine, cosine, or the tangent. Since the distance L is very difficult to calculate because we're going up to the sun, then it's more easy if we just calculate in terms of the horizontal and the vertical, and so we can make it in terms of x and 150. Okay, so this is the opposite and this is the adjacent to the angle, so we're going to use the tangent function. Okay, so the tangent of theta is going to be equals to 150 over x. But now, since we want the behavior of theta instead of the behavior of any of the sides, then we can create a function as theta is equals to the tangent of -1 of 150 over x. And so now that's going to give me a function that I can put the theta angle in terms. Okay, and given that I have that function now I can check the variation using the derivative. So first we can express theta as a function of the shadow length s, and we can compute the variation of theta with respect to s when, let's say, x is equals to 100, and explain what the rate of change is going to mean. So let's do that by using this function. So we have theta is equals tangent to the -1 of 150 over x, right? And notice that this is going to become this type of function, where the farther away that we go in the shadow, the smaller that the angle is going to be. And so from here, you can, of course, use the trigonometric derivative to get more information on the rate of change. All right, so now let's respond to the second interrogant. This is one that we're missing. So we have tangent equals theta equals tangent to the -1 over 100 over x, and so we can calculate the theta dx as the derivative of the inverse function. Notice that that's going to be 1 plus, and normally it will be x squared, but we have a different thing here. We have a different variable. 150 over x is square, and so because that's what we have here, that's what's going to go in there. And now we're going to multiply by the chain rule, which is the derivative of 150 divided by x. And that's going to be -150 divided by x squared. If you're wondering how do I get that very quick, remember that 1 over x can be seen as s to the -1. And so the derivative of that is minus x to the -2, which is equivalent to 1 over x squared, and then multiply by 150. Okay. Now, we have the theta dx now, and so we can calculate what that value is going to be when we get to 100 feet. And so this is going to give me the variation of the angle with respect to the shadow when the shadow is 200 feet. And that's going to be 1 over 1 plus 150 over 200 square minus 150 over 200 square. And of course, here it's a matter of simplifying what that value is going to be. And I leave that calculation to you. But the important thing is that in here, again, we can make the interpretation of the rate of change of whatever theta is, which is the angle of the sun with respect the shadow. Okay, like if the shadow is moving this much, then the angle of inclination must be this. Now, to finish up the part 2 of this video, let's compute some extra examples of taking trigonometric inverse and calculating their derivatives. So we go here to the board. Initially, we're going to go for minus 1 of x plus 2. And again, the derivative of this, once that you know it, you can use it. So this is going to be 1 plus something square, and that something is going to be this, so x plus 2 square. And then we're going to use the chain rule for the x plus 2. Fortunately, there's just going to be 1, so this is just going to be 1 over 1 plus x plus 2 x squared. So that's a very simple derivative. Now, b, we're using secant. So we have secant or arcsecant to the arcsecant of x squared minus 7. If we take the derivative of this, remember the derivative in the secant is going to be 1 over absolute value of x and x squared minus 1 normally. Oh, but here we have x squared minus 7. So it means that we need to change that x and compose with x squared minus 7. So x squared minus 7 in the absolute value in x squared minus 7 x squared minus 1. And that will be the secant. Now, for the cosecant, notice that we have a minus of difference. So normally, if we have cosecant of x, then y prime is just going to be 1 over the absolute minus 1 over the absolute value, x squared minus 1. This is the cosecant, the derivative of the cosecant to the minus 1. Now, because let's call this y1. No, so now, if y equals cosecant to the minus 1 of e to the x, then we have a composition and we have a chain rule. And y prime is going to be the same thing, minus 1 over, but now the absolute value of x is going to have instead absolute value of e to the x. And now this is going to be e to the x squared, and the composition minus 1. We also have a chain rule going on in here because we have the function e to the x. So we gotta multiply at the end by the derivative of e to the x, which is e to the x. Okay. Last but not least, we have cosine to the minus 1 of square root of x. Cosine to the minus 1 of square root of x. And so again, recall that this is very similar to the one of the sine, but with a minus. So we're going to be able to do it very quick. Y prime is going to be 1 minus 1 over a square root, and is 1 minus x squared usually. But because we have a square root here, so square root of x, x squared. And then we're going to multiply by the chain rule, which is the derivative of the square root of x, which is going to be 1 over 2 square root of x. We can simplify this. This is going to become an x, and so this is minus 1 over 1 minus x times 1 over 2 square root of x, or simplifying even further, we can see this as minus 1 over 2 square root of x square root of 1 minus x. And that is what you can do with the derivative of inverse trigonometric functions.